day, I am Bren, and in these set of videos, I will be showing you the practical aspects of doing voltammetry in non-aqueous solutions. For the first part, we'll be observing the wide potential window that can be accessed using non-aqueous solvents and how it is influenced with the presence of water or oxygen. Then for the other video, we will look at the behavior of a redox probe in these non-aqueous solutions. And then for the last part, we will combine our learnings and see the voltammetry of fullerene in the same non-aqueous solutions. I hope you will enjoy this. Let's get to it. As expected in electrochemistry, the choice of your working electrode, your reference electrode, and your counter electrode will be vital for the results of your analysis. So if you want to revisit that knowledge, there is a separate video on this, which is also available in this platform. After ensuring that your working electrode is clean and that you have chosen the appropriate reference electrode, another thing to consider is the choice of your actual non-aqueous solvent and the electrolyte. Now, it is good to remember that the potential window that can be accessed with your chosen non-aqueous solvent and the electrolyte should be wider than the potential window where you would expect your analyte to respond. So in our case, our chosen non-aqueous solvent is your dried acetonitrile, and our chosen electrolyte is your tetrabutyl ammonium hexafluorophosphate. After placing all the electrodes correctly with your potentiostat, now we are ready to do your cyclic voltammetry. So our potential window for this non-aqueous system that we are using is from -2 to 0.1. With our scan rate of 100 millivolts per second, once we start cyclic voltammetry, scanning towards the negative potential, since we were learning to look for the reduction of the presence of oxygen, we will then see a corresponding reduction peak, as you can see here, at approximately -1.2 volts. And that once we reverse the scan towards the positive potential, we will then see a corresponding oxidation peak for this process at approximately 0.4 volts. So the response of oxygen here is quite obvious, and if your analyte reacts or shows the response within the same potential window, then that will be a potential problem. To address this influence of oxygen, especially in battery-related research, they do their experiments in a glove box wherein it's controlled, the oxygen is very minimal. Now in our case, as you can see in our Faraday cage, what we'll try to do is to degas our solution with argon and then try to cover our cell, so leaving a blanket of argon in there as well, just to make sure that we are preventing the presence of oxygen in our system. And then we'll do another cyclic voltammetry to see the effect of removing the oxygen. After degassing, as you can see, there is no peak response that we observe, very different from what we've seen earlier when we have not degassed our solutions yet. And to be very visual, we will try to add now our previous CV so that we can see the difference in the current ranges and the actual response that we expect after degassing the solution. For our final step, we'd like to see the effects of water and see the importance of having dried organic solvents for our voltammetry in non-aqueous solutions. So for this part, we'll try to simulate that by adding a few microliters of distilled water into our cell. So we'll just start CV here and trying to scan towards the negative potential. And for us to see the actual difference with our responses from the previous two steps that we've done so far, we'll try to add the other results that we've had earlier. So with oxygen, and then once after degassing it. We will then see clearly the difference of the response with water. So the one in green here, as you can see, is without the oxygen, so that's after the degassing. The one in red that you would see is with the presence of oxygen, so very obvious response of oxygen within our potential window. And then the one that's currently running now is of course the response that we get once we've added water, even though we've still degassed our cell. So the presence of water in your system would definitely have an impact, especially if your expected results or response of your analyte is within this potential window. So it is important to make sure to remove the water, if not use dried organic solvents, and then try to remove oxygen from your system if necessary.